So friend, we have seen how we can apply first law of thermodynamics for a closed system as well as for an open system. For open system, we derived equation which relates enthalpy with kinetic energy, potential energy, and the work which is being done by the system, and the heat which is work being done by the system or on the system, and the heat which is exchanged with the system. Now, when we go to a closed system, the equation for that is nothing but delta U is equal to Q plus W. When we try to apply these equations to ideal gas system, right, we have to apply equations which are based on various kinds of processes. We have already seen constant volume and constant pressure process equations, and what we are going to see today is we are going to extend that to different other kind of processes, including adiabatic process. So let us first revisit the definition of an ideal gas. So what is an ideal gas? Generally, when we discuss ideal gas, something which comes to our mind is a gas which follows PV is equal to nRT. Now this is something which is a characteristic of an ideal gas. So PV is equal to nRT, yes, a gas which is an ideal gas will follow PV is equal to nRT, but that is not something with which we imagine what an ideal gas is. An ideal gas is the one where two molecules which are part of the gas are not impacting the behavior of each other. How cannot they impact the behavior of each other? There are few possibilities. One of the possibilities is that when we keep them away from each other, their presence will not impact, right? This is molecule A and this is molecule B, maybe molecule A itself, right? So there are no forces of attraction, no repulsion, no polarity, nothing coming into picture when their distances are far apart. So this could be understood with the current scenario when we are teaching everybody online. We can see that the students who are sitting at their own place, they are idle in their own behavior. They are not getting impacted by their friends. Comparing that if they are sitting in the classroom. So if they are sitting in a classroom, continuously there is someone who is disturbing you, or who is asking something to you. So your behavior will be impacted by the presence of other molecule or other person. So when we keep them apart, so this happens when the volume is infinite or when the pressure tends to 0. So either the molecules are kept far away from each other so that they don't impact each other, there are no molecular level interactions between them, or they are too busy to interact with each other, so they are in a continuous motion. They are continuously moving from here and there, and they don't bother who is there just besides them. So there also they are in their own behavior, and this happens when the kinetic energy is too high, or we may say when the temperature is too high. So there are two process parameters which can tell you that a gas may behave ideally or not. One is when the pressure is low, another is when the temperature is high. For an individual gas, for a pure gas, this low pressure and high temperature could be relative, like for one gas something which is very high, for the other gas that may not be so. But in general we can say that the low pressure and high temperature would tend to give you ideal gas condition. And how do we imagine how do we say, for example, define ideal gas is that when there are no molecular interaction between them, when a molecule is behaving as in its pure state, it's in its own state, is something where the gas is going to be ideal. Now for such gases, right, we can say that they are not existing. Such gases are not existing. They are hypotheses. But we can develop the equations for ideal gas and then we can apply it to it. And when we compare it with the actual processes, we can compare how the actual process or actual gas is going to behave with respect to an ideal gas. For an ideal gas, what we have is this, which is something which you already know. And most importantly, for an ideal gas, internal energy and enthalpy are only function of temperature. That means when I am trying to calculate delta U and delta H for any given ideal gas, I just have to look in for initial and final temperatures. I am not worried about the type of process. The reason being they are dependent only on temperature, and moreover they can be considered as a state function. And because of that only, what we can do is this. Just look at this figure. Here I have plotted U as a function of V because I know that for a constant volume process, delta U is equal to CV delta T. Now if I look at this particular figure, I say that this particular process, that is one which is represented by B, is a constant volume process. Why it is a constant volume process? Because it's a vertical line. So this is a constant volume process, and for constant volume process we know that delta is equal to CV dt. But on the basis of the statement which we made in the previous slide that U depends only on initial and final temperature, if I am conducting any process which takes place between T1 and T2, which is same as that of this process, that is this T2 and this T1, irrespective of whether the process is constant volume or no. See, both these processes C and D are having changes in initial and final volume, but still the temperature range is T1 to T2, and if the temperature range is from T1 to T2, you can calculate delta U is equal to CV delta T. You don't need to keep the restriction of keeping the process to be a constant volume process for the application of this equation. So for any process of ideal gas, delta U is CV dt irrespective of whether the process is constant volume or not. However, this will be equal to Q only if the process is constant volume or having initial and final volume to be same, which we already discussed in our earlier videos. On the similar lines, you can draw H as a function of P, and then for any given temperature scale T1 and T2, you can say that dH is equal to Cp dt for ideal gas irrespective of the process whether it is constant pressure or not. Correct? Now let us develop some equations for the process calculation of an ideal gas, which will be helpful to us in calculating heat and work interaction for any given problem. So we already know that for a mechanically reversible process, dW is minus P dV, and when I integrate it, it becomes W is equal to integral minus P dV. If I apply to the closed system first law, which is du is equal to dq plus dw, right? Then I write du is equal to dq plus dw. But for an ideal gas, du can always be replaced by Cv dt irrespective of the type of process. So what I do is I replace du with Cv dt. So I got dq plus dw equals to Cv dt, and this can then be written as this, where I can write dq is equal to Cv plus dt minus dw, and minus dw is replaced with pdv. Okay, which can be then written as dq is equal to Cv dt plus replacing Pe with RT by V, I get dq is equal to Cv dt plus RT dV by V, right? I can write dW as minus RT dV by V. So these are some of the equations which I utilize in further slides so that we arrive at some equations for specifying kind of processes. The first one being isothermal process. Now in isothermal process, what happens? Temperature remains constant. So initial temperature and final temperature is same, and since it is an isothermal process, and since temperature remains same and internal energy and enthalpy depends only on temperature, I can straight away say that for any isothermal process, delta U equals to delta H equals to 0. right? And if I apply first law of thermodynamics, I can say delta U is equal to Q plus W, and which I can say Q is equal to minus W, and W can be converted using your mechanically reversible process definition of work, which is integral minus P dV. Since it is an isothermal process, I can convert P into RT by V, and R and T can be taken outside the integral term, and I can integrate dV by V from V1 to V2, and what I get is this equation or these equations. All equations are correct, right? I can say Q is equal to RT ln V2 by V1, and then can say Q is equal to minus W, or I can say Q is equal to minus RT ln P2 by P1, and then say Q is equal to minus W, or I can calculate W as minus RT ln V2 by V1 and say W is equal to minus Q, or I can write W is equal to RT ln P2 by P1, and then I can say W is equal to minus Q. Depending upon what data we have for initial and final state, if I have volumes with me, I'll use these equations or any one of these equations, and if I have P1 and P2, I'll calculate this. Sometimes I have both, that is P1 V1 P2 V2 both. In that case, it's up to me to calculate what I want, right? So this is for an isothermal process, how to calculate delta U, delta H, Q and W, right? Don't need to mug up any of these equations. You can just arrive at them by applying proper way. Isobaric process, we already have seen constant pressure process. So we know that delta U is equal to this, delta H is equal to this. Keep in mind, now I can write delta U is equal to Cv dt for every process, delta H is equal to Cp dt for every process, as long as the process is taking place for an ideal gas. So I don't need to consider the process to be ideal. Okay. For an isobaric process, Q is equal to delta H. So I know delta U, I know delta H, I know Q. So numerically I can find out W by delta is equal to Q plus W. That's it, directly, right? But I can even find W as minus P delta V, right? Integral minus P delta V. Pressure being constant, I can take out pressure outside the integral term, and I can say P delta V. So when I solve a numerical, right, I can use various ways to solve that. There is no set rule for the equations. However, for developing this set of equations, I have arrived delta W is equal to minus RT2 by T1. And in the same way, for an isochoric process or a constant volume process, work is going to be 0 because there is no change in volume. Delta U is this, delta H is this, and delta is equal to Q plus W, so that becomes equals to Q. So this is for an isochoric process. And last but not the least, adiabatic processes. For adiabatic processes, we can say that there is the Q is 0, and since Q is 0, dq is 0, right? So I can apply du is equal to dw or Cv dt is equal to minus P dV. I am just deriving some equation which will be helpful to us for developing expressions for polytropic processes, or for developing the equation relating pressure and volume and temperature. Otherwise, calculation of delta U, Q, W and delta H can be done in a much simpler way using some numerical value, which I think we will be able to see when we solve a problem. So I can write this as dt by t. From this I can replace P is equal to RT by V, and then this can be written as dt by t equal to minus R upon Cv. Cp by Cv can be written as gamma, and I can I can integrate this to this expression which relates T and V for initial and final value. Similarly, I can relate T with P and P with V, and I get this equation. So when I have an adiabatic process, I can apply any of these equations depending upon the process parameters I have, and I can calculate the other term, right? And if I want to calculate the work for adiabatic process, I can calculate it like this. I can replace Cv by this equation. Substituting this Cv here, I get W. So this is my equation for work for an adiabatic process. As I already mentioned, that we can utilize separate way to calculate numerical values. However, this will be helpful to us to calculate the work for a polytropic process, which is given by this. So this is for an adiabatic process where gamma is Cp by Cv, and this is for a polytropic process. So we'll use these equations and solve few problems when we meet in our next video. Thank you.